Unit 8, Chemical Reactions. So we're going to begin talking in this unit about some important terms. So the first one is chemical equation. Okay, so a chemical equation represents, with symbols and formulas, the reactants and the products in the chemical reaction. And what are reactants? Reactants are chemicals that undergo a chemical change. And then products. What are products? Products are the chemicals that are produced as a result of a chemical reaction. So let me just do a hypothetical equation. I'm gonna do it here on the top. Okay, so let's say that we had chemical reaction and we have some hypothetical elements or substances. A is one chemical. B is another chemical. And then they react together and they become A, B. So this arrow, and we'll talk about a little bit more later on as well, but the arrow tells you the direction of the chemical reaction. So if you see an arrow like this, the substances to the left of it are the reactants. The substances to the right of it are the product, or products. Okay? And then sometimes you'll see reactions like this. Let's say we have A plus B, and you might see something that looks like this. What this is saying is that the reaction is reversible. So if the reaction goes from left to right, this would be the reactants, and this would be the product. But if you look here, where it goes in this direction, then these would be the reactants. All right, the reactant, and this would be the product. So it's important to look at the direction of the arrows, and that'll get an indication of the direction of the reaction. Okay, so if we look at the equation, all right, the equations are important. They tell us a lot about the chemical reactions that are occurring. Okay, so if you look at the requirements for a chemical equation, the chemical equation, and I'm reading this part over here, the chemical equation must represent all the known facts, including the identity of the products and all the reactants. Okay, so all the products and the reactants. The equation must contain the correct formula for all reactants and products. And the law of conservation of matter must be satisfied. Okay, these are three important requirements for a properly written chemical equation. So here, the law of conservation of matter, what does that say? Or what does it mean? So the law of conservation of matter states that matter cannot be created or destroyed under ordinary physical or chemical changes. So the law of conservation of matter can be applied to chemical equations with a law known as the law of conservation of mass, which states that in a closed system, and what is a closed system? That's a system where matter cannot enter or escape. The number of atoms must be the same on the reactant and the product side of a reaction. In a closed system, no matter is moving in nor moving out. Okay? So if I go back to the chemical equation, and let's apply that for a second or discuss it. Okay, so again, if I have A plus B, right? So you have two chemicals, A and B. These are hypothetical. And then you produce A, B. All right. Let's say that I have 1 mole of A and 1 mole of B, right? 1 mole of A, 1 mole of B. Then and this is my reactant side, the product must also contain 1 mole of A and 1 mole of B. Okay, so you always have to have the same number of atoms, the same mass on the product and reactant side. So, and I'm going to turn this equation around. Let's say you have A, B, and you produce A plus B, right? So here I have 1 mole of A, 1 mole of B, and on this side here, I'm going to have 1 mole of A and 1 mole of B. So there's going to be the same on both sides. So 1 mole of A and 1 mole of B. Let's say that we had a chemical reaction in which we have the chemicals in other than a 1-to-1 ratio. So let's say that you have A2 and B. So here we have we have 2 A's for every B. And then I make a chemical like this AB. Okay? So if you look at this, and let's do it in the inventory, what's here. I have 2 A's and 1 B on my reactant side. On the product side, I have 1 A and 1 B. So here, this chemical reaction is not written properly. And why is that? Because the amount of matter, the number of atoms of each of the element, is not the same on the reactant and product side. So I have to account for that. I can't just this A, right? The A that's missing on my product side, I have to account for it. So what I'm going to do is I'm just going to put a plus A to say that, right, I formed AB. I can't form another A and B because there's not enough B's. Okay, so I've accounted for the A. Now if I go on, look at the reactant side, I have 2 A's. I have 1 B. Now if I look on the product side, I have 2 A's. Right? I just added 1 on that side to account for it. Right? And then I have 1 B. So I've abided by, right, the law of conservation of matter, so that I have the same on both sides. You always have to. Right? Anytime you don't have the same on both sides of the reaction, then you're not abiding by that, right? The law of conservation of matter, and which would mean that you have a chemical reaction, chemical equation that's written improperly. Always be aware of that. That's one of the major things that you'll see, that mistakes that are done are made when we talk about chemical reactions. Now, when we look at chemical equations that we write, you're going to be using elements that occur in pairs. So I'm looking here, number 6. We call these diatomic elements. All right, so the following elements are found as diatomic elements. When not bonded to other types of elements, they must be written in the reaction as pairs. So if you look here, H, hydrogen, if you have hydrogen gas, it will exist as H2. Nitrogen, so the nitrogen you find in air, it's not a single atom. They're all bonded together in pairs. Fluorine, oxygen, so the oxygen you breathe is O2. Iodine, chlorine, and bromine. Those all are found in diatomic molecules. So for instance, let's look at water. All right, we all drink water. Okay, so if you look at water, water has hydrogen and oxygen. So we know hydrogen plus oxygen make up H2O or water. Now, if you look at this, and I'm going to go down to this, down here, and if I look there, what I'll see is that hydrogen and oxygen, they exist as pairs. They're diatomic molecules. So I cannot write them in an equation as just single atoms. I have to write them as pairs. But if you look, what you notice is that the number of oxygen and hydrogens, right, are they the same? So let's take a look at this. Okay, if I look at the hydrogen, how many hydrogens do I have on this side? So I have 2 of them. And oxygen, I have 2 of them. But look on the product side. I have 2 hydrogens, but here's the problem. If I look at the oxygen, there's only 1 on this side. I've broken the law of conservation of matter, so I need to make sure I have the same on both sides. And this is where balancing chemical equations, where we start introducing it. I need to do something so that I write this equation to account for all the elements. They can't just disappear. So if I look here, I have 2 hydrogens, 2 oxygens. Now I cannot change the subscript. All right, so this right here, I can't change the O2. Right, the 2, and I can't change the 2. You never can change the subscripts when we write down elements. But what I can do is I can put a coefficient. So when we do that, we're going to put a number in front of the element. So if I look here, I need 2 oxygens on the product side. So what I can do is put a 2 in front of here. And then let's look at how many we have now. On the reactant side, we still have 2 hydrogens and 2 oxygens. But on the product side, I don't have 2 hydrogens anymore, I have 4. But I do have 2 oxygens. So I've fixed one problem. But what I've done is I've created another one, right? So what I need to do now is figure out how am I going to change it so that I have the same number of hydrogens on both sides. So we saw when we put 2 in front of H2O, we just doubled everything, right? Because when we write 2H2O, if you write 2H2O, this is the same as writing H2O plus H2O, right? By putting that the coefficient in front of it. So what I'm going to do is I'm going to put 2 in front of the H2. And when I do that, I've now doubled the number of hydrogen atoms. And instead of having 2, right, because 2 times H2 is going to give me 4. So now I have 4 hydrogens, right, on my reactant side, and I have 4 hydrogens on my product side. I have 2 oxygens on my reactant side. I have 2 oxygens on my product side. I now have a balanced equation. In other words, The amount of matter is the same on both sides of this equation, which is exactly what I want. So this equation would now be written properly and abide by the law of conservation of matter and the law of conservation of mass. In addition, what I've done is I've used diatomic molecules, which is the correct way, because if the elements are by themselves, if hydrogen is by itself and oxygen is by itself, in other words, not bonded to anything else, they have to exist as diatomic molecules. You'll notice over here in H2O, water, oxygen is by itself. There's only one of them, right? There's a 2-to-1 ratio between hydrogen and oxygens. That's because when oxygen is bonded to other elements, it can exist by itself. All right? So let's continue. So if you look at word equations, so word and formula equations, and because a lot of times that's how we write, we'll write down chemical reactions, as we'll talk about, or use word equations. So a word equation, the reactants and products in a chemical reaction are represented by words. So here's an example. Methane plus oxygen produces carbon dioxide and water. And this is a combustion reaction. So that's when you burn methane with oxygen, you produce carbon dioxide and water. A formula equation represents the reactants and the products of a chemical reaction by their symbols of formulas. Okay, so we said methane plus oxygen equals carbon dioxide and water. So methane is C. All right, so this is my CH, which we write. Sorry, this is methane. We can write that as CH4. And then we add oxygen to it. Remember, oxygen exists as a diatomic molecule, O2. And we said it produces carbon dioxide, CO2 plus. And actually, let me move that, this CO2. Okay, so we said it makes CO2 plus H2O. Is this chemical reaction balanced? No. And I'm not, so it doesn't meet the conservation of matter. And what we'll do is we'll use this as an example later on for balancing chemical equations when we talk about how to do it. When we write a formula equation, we're going to use different symbols. In this table here, this has some of the symbols that we use. And so the first one, the arrow, that tells me that it yields. So it's showing what the product is. So the arrow shows what the reaction yields. In other words, what are the products? This shows you a reversible reaction. And then the S, this tells you that the product or the reactants are in a solid state. And then an arrow going down, this is an alternate symbol used to indicate a solid, used only to indicate a precipitate formed in a solution. And then this is this symbol. All right, so this little L over here, that indicates that the reactant or product is in a liquid state. I forgot to leave a space there for it. And then AQ, that means it's an aqueous solution. In other words, you dissolve a substance in water. And then G just indicates that the product or reactant is in a gaseous state. And then the arrow going up indicates a gaseous product or reactant. All right, it's an alternative for using the G in the parentheses. And let's look at some more. Okay, so these are some additional letters or symbols that indicate something in a chemical reaction. So if you look at PT, right, you got the arrow PT above it. The formula written above or below the yield sign. Right, so you can put it here. You also can put it down here. Indicates the use of a catalyst. What's a catalyst? A catalyst is a substance right, that speeds up a chemical reaction. It does this by lowering the reaction or the energy needed to initiate a chemical reaction. So a chemical okay, and a catalyst is not consumed in a chemical reaction. Right, so they're not consumed in a chemical reaction. In other words, your catalyst, if there's a catalyst that's driving a chemical reaction, it lowers the activation energy. In other words, it lowers the amount of energy that's required to initiate a chemical reaction, and it does not become part of the product. And it can be used over and over and over again. So you may have heard this in a car. You have a catalytic converter in the exhaust system, right? And it's important for, it helps break down nitric oxide, so it's for pollution control. And then you have this other one here, right? You have the delta symbol or the word heat above a reaction indicating that heat is supplied to the reaction. And then you have a positive, so plus sign, that's used to separate products or two or more reactants. All right, now we're looking at some examples of balancing chemical reactions. This is showing, so back to what that we talked about previously. This is showing your methane, CH4, and it looks like this. It's a simple molecule. Yeah, this is showing the structural formula. CH4 methane plus oxygen yields carbon dioxide and water. This is not balanced. So what I did down here, is I balanced it. How did I do that? If you compare this unbalanced chemical equation with this one here, you'll notice that it put a coefficient of 2 in front of the oxygen. So we have 4 oxygens on this side. If you look here on this side, you have 2 oxygens here, and there's 2 water molecules, so you have 2 oxygens there, so that's 4 oxygens. There's 1 carbon here, 1 carbon here, and if I look at the number of hydrogens, we have 4 hydrogens on this side, because you have 2 H2, and we have 4 hydrogens on this side. And then the oxygens, I have 2 oxygens here. Sorry, not 2, I have 4 oxygens here. And this side you have 2 oxygens here, and then I have 2 oxygens here because it's 2 H2O, So I have 4 oxygens on both sides. So the number of elements are the same on both sides. And really, there are guidelines you can use for balancing chemical reactions, but it's trial and error. You change the coefficients. You can't change the subscripts, but you can change the coefficients, and you change them to try and make it so that you have the same on the reactant and product side. Right? It takes practice. So I mentioned this before, but if I look at a reversible reaction, right, that's a chemical reaction in which the products can reform the original reactants. Right, the reaction can go back and forth. Okay, so now the significance of a chemical equation. All right, what is it telling me? So here, the amounts of reactants or products show the smallest number of atoms and ions or molecules that will satisfy the laws of conservation of matter. And then the ratio of reactants or products, right, shows the relative amount of products and reactants. And the reverse reactions, the same amount of and kinds of atoms are located on both sides of the equation. So this part here, this A and B, okay, let's talk about that for a second. So the amounts of the reactants and products, right, shows the smallest number of atoms and ions or molecules that will satisfy the law of conservation of matter. And the ratio of reactants and products shows the relative amounts of products and reactants. What does that actually mean? So let's take a look at that for a second. Okay, let me do an example up here. And let's look at water, since we've talked about that before, and it's probably an easy example to relate to. Right? Remember, H2O, right, is water, and we make out of hydrogen. I have to write as H2 because it's a diatomic molecule. Oxygen I have to write as O2 because that's another diatomic molecule. I'm showing this arrow going to the right. It shows me what I yield from this reaction, which is H2O. And remember, this reaction is not balanced, so I need to put a 2 in front of there to get my 4 hydrogens and 2 oxygens. And then I'm going to put 2 in front of there. So the coefficients, the 2 is the coefficient, right? If you look, there are, if you look at the ratio, if you look at the ratio, you have a 2-to-1 ratio. In other words, I have four hydrogens, but for every water molecule I produce. So I have 2 hydrogens for each water molecule I produce. It's a 2-to-1 ratio for hydrogens and water. Okay, and if you look at oxygen, it's a 1-to-1 ratio because there's 2 oxygens on this side and there's 2 water molecules on this side. So the ratio of oxygen to water is 1-to-1. It makes sense because if you look in this water molecule, there's 2 hydrogens for each oxygen. The equation is going to reflect that. But so we have that ratio. So let's say that I wrote the equation like this. All right. Let's see. Oops, I ruined that. Let's reform my. All right, and I have O2. let's say that I write the equation like this, where let me erase this coefficient here, erase this coefficient here. And I did it so I had 4 So if you look, you'll see now I have 8 hydrogens on this side. I have 2 oxygens on this side. And on this side I have 8 hydrogens and 2 oxygens. Actually, I made a mistake there. I have 4 oxygens. All right, it's not balanced, so I need to put a 2 in front of here. But if you look, all right, so I have 4 oxygens on this side. And I have 8 hydrogens on this side and 4 oxygens on this side. And this I have 8 hydrogens and I have 4 oxygens. So if you look, this is balanced. But is it properly written? No. We said that you have to have the lowest whole number ratios when we write a chemical equation. They're the right ratios and it's balanced. But we need to show it when we write it. It needs to be properly written so you have the smallest coefficients that you possibly can have. So when we wrote it before, right, if you recall, we wrote it so it said 2H2 plus O2 is going to yield 2H2O, which was balanced. So if you look at this is not written properly because I need to have the ratio, the smallest whole number ratio of the elements in my products and reactants. This is written where the smallest whole number ratios are written. Okay, so this is properly written. This is not. So if you go back to here, we said that you're supposed to have the amounts of reactants show the smallest number of atoms and ions or molecules, right? In addition, we said that the reactants and products show the relative amount of the reactants and products, and it has to be the smallest whole number ratio. Okay? Balancing chemical equations. And there's no magic answer or methodology to balancing a chemical equation. And I'll try to, during our lecture, the live session, we'll try to work together to balance chemical equations. So some guidelines for balancing chemical equations. So here I have it over here. Step A, identify the names of the reactants and products and write a word equation. B, substitute correct formulas for the names of the reactants and products and write the formula equation. And then C, adjust the coefficients in the formula equation so the law of conservation of mass is satisfied. So how do we generally do this? So start by balancing the different types of atoms one at a time. Right? Don't try to do two or three at a time. Focus on one first. And then so first balance the type of atoms that appear only once on each side of the equation. Then balance the polyatomic ions that appear on both sides of the equation as a single unit. And then finally balance hydrogen atoms and oxygen atoms after all other elements have been balanced. So that's a good rule of thumb when you're balancing chemical equations. And then finally, you want to check yourself. Make sure you have it written properly. So you're going to count the atoms to be sure the equation is balanced. Always check them to make sure that they are balanced when you have it written. All right? Now, types of chemical reactions. There's more than one kind of, or one type of chemical reaction. All right? So, a synthesis reaction, and that's actually what I showed you before. It's a combination of two or more elements to form a binary compound. So, like water, you have H2 plus O2 is yielding EH2O. This is a combination reaction. It's a synthesis reaction where you're taking and combining hydrogen and oxygen together to form water. All right, very simple. And then let's look at the next page for some other types of reactions. And this is showing an example up here of my synthesis reaction. Sodium and chlorine makes sodium chloride. You'll need to be able to predict the product of a synthesis reaction involving the combination of two or more elements to produce a binary compound. You will need to recognize any other synthesis reaction. So reactions of elements with oxygen produce oxides of oxygen of an element. Think of rust to iron, right? You have Fe is iron. If I add oxygen to it, I'm going to make Fe2O3. All right, so I'm going to make iron oxide. And obviously this is not a balanced chemical equation. This would be an oxide of iron oxide. Reactions of two nonmetals form covalent compounds. Why? Because the electronegativity is relatively close, so the atoms are going to share valence electrons. So you're going to produce a covalent compound. And then reactions of metals with nonmetals other than oxygen often produce ionic compounds. And if you recall, metals have a very low electronegativity, but the nonmetals have relatively high electronegativities. And that's why the reactions occur as they do, where you have metals and nonmetals, it's going to be ionic. Finally, synthesis reactions of oxide. Oxides of active metals react with water, right? And iron oxide is an example, to produce metal hydroxides, also nonmetal oxides. H2O is going to use oxyacids as an example. All right, another type of reaction is a decomposition reaction. So a single compound undergoes a reaction that produces two or more simpler substances. That would be a decomposition reaction. An example, right? This is breaking water apart. 2H2O is going to produce, mercury oxide. 2HGO, right? And the S means it's in the solid state. Is going to yield 2 mercuries in a gas state, liquid state, and 2 oxygen in a gas state. All right, so this is an example of actually breaking this apart and producing hydrogen and oxygen. Mercury and oxygen. Metal carbonates. Metal carbonates heated produce metal oxides and carbon dioxide. So examples, CaCO3, right? The S means it's solid. That's going to be heat. CaO, The S means a solid. Carbon dioxide is kept or made as a byproduct. Okay. Metal hydrides decompose when heated to give metal oxides and water. Metallic chlorates. All right, so metal chlorates, when heated, decomposes to a metal and a chlorate. All right, so acids, certain acids decompose to non-metallic oxides in water. Then we have a single replacement reaction. So one element replaces a similar element in a compound. Replacement of a compound by a more reactive metal. So when you have a single replacement, if I have a metal that's less reactive, and a more reactive metal shows up, it's going to take the place of the less reactive metal. Replacement of hydrogen in water by a metal. Most active metals react vigorously with water to form a metal hydroxide and hydrogen. Replacement of hydrogen in an acid by metal. Most active metals most active metals react with certain acids to form hydrogen gas. And actually, that's one of the dangers of having metal interacting with hydrogen. Interacting with acids, because it produces hydrogen, and hydrogen gas is very explosive. So you can create some safety issues if you're doing replacement of hydrogen in an acid by metal. All right. And then replacement of hydrogens. All right, so let's stop there. Go to page 4. All right, halogens replace another halogen. Fluorine can replace other halogens. More reactive halogens can replace less active halogens, or less active ones. A double replacement reaction. Right? In a double replacement reaction, the ions of two compounds exchange places in an aqueous solution to form two new compounds. It involves the change of positive ions between two compounds. Generally, double replacement reactions involve the formation of a precipitate, the formation of gas, and the production of a molecular compound. Now, another reaction that we should be aware of is a combustion reaction. We see these all the time. Anytime you see something burning, that's going to be a combustion reaction. All right? So a combustion reaction, a substance combines with oxygen, releasing a large amount of energy in the form of light and heat. Most combustion reactions involve hydrocarbons, which produce carbon dioxide and water when fully combusted. Hydrocarbons are composed of the elements carbon and hydrogen. If combustion is incomplete element, Okay. All right, so this is the rest of the table for the activity series. If you look at the top, the elements that towards the top are the most reactive. The elements towards the bottom are the least reactive. So you'll see on here lithium, which is at the top. That is, of these metals, of these these elements, they're the most reactive. So the elements towards the top have a tendency to replace those further down in a chemical reaction. So if I have something, let's say that I have mercury bonded with something. Let's say we have AHG, right? A is made up, Hg is mercury, and another chemical comes around. Let's say you have aluminum, Al. If the aluminum goes by where the mercury is, because aluminum is more reactive than mercury, it will take the place of mercury. So you have AHG. And okay, so these are less reactive. All right, and they're going to replace. You'll see the elements that are more reactive replacing the elements that are less reactive in a chemical reaction. Okay, so let's start our introduction to thermal energy and the gas laws. And let's start talking about some definitions. Thermal energy, what is it? Thermal energy is the sum of kinetic and potential energies of particles of a system. They exist independent of the medium. And so another term, temperature. We hear it all the time. What does it actually mean? Temperature is a measure of the average kinetic energy of objects or systems particles. And so this is an indication of the worth of something. So it's really the average kinetic energy in matter. That would be the temperature. The higher the temperature, the more kinetic energy that's going to be in that system. All right. And really, the molecules are going to be vibrating or moving more frequently. Now, if you look at the thermal energy, right? So the average kinetic energy will vary with each medium being measured. Therefore, temperature is dependent on the medium. Now, what does that mean? That means that I could add the same amount of heat to two substances, but one substance will have a higher temperature than the other. So the medium is going to have an impact on the temperature, how fast or how slow the temperature is going to rise. Thermal equilibrium. What is thermal equilibrium? Heat always moves from warmer regions to cooler regions, right? So when you open a door and you say you're laying the cold in, that's actually not true. Because cold is just absence of heat. And heat always moves from warmer or hotter areas to cooler areas. So during the winter, when you open the door up, it's not actually the cold that's coming in, it's the heat that's moving out. So there's a net movement of heat from warmer to cooler regions, and this occurs until the objects each reach the same temperature. And when both objects reach the same temperature, there is no net movement of heat, right? This heat still moves between them, but the same amount moves back and forth. The objects are said to be at thermal equilibrium. Thermology is the science of temperature and its measurement. A thermometer, this is a device that we use to measure the temperature of an object or system. Right? Remember, temperature is the average kinetic energy. Now, heat transfer. So you've heard these terms, and these terms are actually helpful in, if you think about humans, how we cool and heat ourselves. So heat energy can be transferred in three different ways. Thermal conduction. This occurs when thermal energy is transferred without any net movement of material itself. This can also be described that the thermal energy is transferred as particles collide, passing the thermal energy as a result of these collisions. Once two or more objects in which thermal energy transfer are occurring reach the same temperature, then there's no net thermal energy transfer. Thermal equilibrium has been reached. So in thermal conduction, you have to have the objects come in contact in order for the heat to be transferred from one object to another. And that transfer of heat will occur continuously until they both reach the same temperature. And then in other words, they'll still be moving, but there'll be no net movement. So the same amount of heat that moves from one object, the same amount of heat will move back to the other object. Convection. This occurs when there is movement of a fluid, such as a gas or liquid, from one location to another, resulting from temperature differences. The greater the temperature differences between locations, the greater the convection will be. So if you have a convection oven, that occurs by moving heated air throughout the oven. And so that heated air is moving the heat around the inside of that oven. Radiation requires neither contact or mass flow. This is the transfer of energy through electromagnetic waves. All right, so radiation, this is how heat is transferred from the sun. Thermal conductions or thermal insulators. So you have two substances, can be one of two things. They can be a thermal conductor, right? This is a material that actually conducts energy, heat energy. Or a thermal insulator. This is a material that's poor at conducting thermal energy. So, how do you know whether something is a conductor or thermal conductor or thermal insulator? If you put your hand on something, let's say like metal, and it feels cool, that's because it's really pulling the heat away from your hand. In other words, your hand is moving, remember it moves from warmer to cooler areas. It's going to move from your hand to the metal, right? And so metals are good conductors. But if you have something that's a thermal insulator, heat doesn't move as quickly from your hand to that object, so it's not going to feel as cold, right? And it'll act as an insulator. So like if you think of a jacket, let's say the weather's getting colder now, though, a jacket, you have an insulator in it. And it's an insulator because heat doesn't travel very quickly through it. And that's good for us because that keeps us warm. All right? So those are some terms that we are helpful for heat. Understand heat transfer. The gas laws of kinetic energy. All right? So the concept of air pressure evolved. And now, first of all, why are we actually looking at the gas laws when there's a couple of reasons. It's an important part of chemistry, but if you think about in human anatomy and physiology, you have a gas called air that passes in and out of your lungs. The gas laws help determine the movement of that gas. So if you look at at this right here, right, the concept of air pressure evolved from our observation of lift pumps, which were limited to lifting, so they're used to lift water. They're limited to lifting water about 34 feet. It was initially thought that water moved up the lift so a vacuum would not form. There should be lift. This was challenged by Evangelista Torricelli, who proposed that the atmospheric pressure exerted on water at the bottom of the pump forced the water out of the pump at the top. He also reasoned that since mercury is 14 times more dense than water, a column of mercury 1/14 as high as water would be supported by the atmospheric pressure, which was supported through observation. So what should you walk away from this? Because I'm not going to test you on this part. This is just showing you some history on the development of our gas laws. So how did we learn it? All right. Now, what are the gas laws? So there's four. There's a few gas laws that we're going to talk about. So this the first gas law we'll talk about is called Boyles Law. All right. So Boyles Law, it states that temperature and the number of atoms or molecules are held constant. So if you have an increase in the pressure, causes a decrease in the volume, or a decrease in the pressure causes an increase in the volume. So let's look at Charles' law. Well, first, this got messed up a little bit. It should be V1 over T1 equals V2 over T2. And again, this is you're talking about the same volume, the same number of atoms or molecules on either side of this, because you're talking about the before and after. So let's look at the law itself. So Charles' law, pressure and the number of atoms, molecules are held constant. So you see there's volume and temperature, we don't see pressure. So pressure is held constant. And the number of atoms or molecules is constant. They don't change. But our volume and temperature can change. So the volume, pressure, and for some reason I put pressure in here, volume and temperature are directly proportional. When the temperature increases, the volume increases. And when the temperature decreases, the volume decreases. And temperature is always expressed in Kelvin, the Kelvin scale. So what this means is, and we know this from looking at something like a hot air balloon, if you increase the temperature, the volume is going to increase. And you may have seen demonstrations where they take a balloon and put it in liquid nitrogen, and the balloon shrinks. So the temperature decreases, the volume is going to decrease. So, and our temperature is always going to be in Kelvin. All right. So that's Charles' law. Now, Gay-Lussac's law. This law states that the pressure of a fixed mass of a gas varies directly with the Kelvin temperature at constant volume. In other words, if the temperature increases, the pressure is going to increase. If the temperature decreases, the pressure is going to decrease. And again, the temperature in this one has to be in Kelvin. And then the ideal gas law. This law can be used to determine the pressure, the volume, the number of moles. So P is for pressure, V is for moles, and V is for volume, N is for moles, and the R is a constant, which is 8.314 joules per mole degree Kelvin. Kelvin. So when pressure is measured in pascals, volume is in cubic meters, and Kelvin in temperature. Temperature in kelvins. So the gas laws, I'll have a couple of them on the test, but not a lot. I really want you to understand them more than anything else. And I'll try to give some examples of some equations during the live session. And finally, the kinetic theory of gases. Kinetic theory states that all matter is made up of atoms, and these atoms are in constant random motion. The kinetic theory of gases explains why gases behave in a way they do, thereby connecting the microscopic and macroscopic properties of gases. Principles assumptions of an ideal gas for the kinetic theory of gases. So when we talk about gases, generally we're talking about what's referred to as an ideal gas. And so when we talk about the gas laws, it's really looking at an ideal gas. So in an ideal gas is thought of as a gas that consists of many identical molecules. The molecules are very far apart in comparison to their size. That is, the volume of the molecules is negligible when compared to the size of the container. The direction of motion of any molecule is random. On average, no direction is preferred above another, and the molecules move with a variety of speeds. And the molecules are treated as if they were hard spheres. And then finally, molecules obey Newton's laws of motion. All right. So when we talk about the gas laws, we're really talking about an ideal gas. And so that's it for the gases. And so it'll probably be Boyle's Law, because that one relates most to human anatomy and physiology, that I'll focus on as far as questions. The other laws, gas laws, I will touch on a little bit, and you should understand the relationship between temperature, pressure, and volume in the different gas laws. All right. Thank you. And if you have any questions, please ask me during the live session.